And here you may want to pause the video while you read through the problem. Once again, we can organize this in a chart. We're going to have your rate times your time is equal to your distance. Rate times time is equal to distance. We have two rates. We have the rate of the one runner being 6. We have the rate of the second runner being 8. Now it says how long will it take the first runner, or how long will it take the second runner to reach the first? So you're looking for time. So I would say you're going to want to go ahead and let your variable represent what you're looking for, which is how long for the second runner, which is this one right here. Now when you're talking about your first runner, are they running for a longer period of time or a shorter period of time? Well, they started 5 minutes before, so it's really 5 minutes longer is what they're running. So you're going to have t plus. Now some of you might be tempted to go ahead and add 5. However, as you look at the units here, the units of your rate is miles per hour, miles per hour. So that means your time needs to be in hours since your rate is miles per hour. So you got to think, okay, 5 minutes is how much of an hour? 5 minutes is really just 1/12 of an hour. You could just go ahead and take your 5 over 60 and reduce that down. Once again, in each case, we have 2 of the 3 boxes filled out, so you can always fill out your third box by following the operations at the top up here. Do the same thing here, your 6 times your stuff here. Now, your equation, once again, will always come from what we have over here. Well, I shouldn't say always, but for the most part will be coming from over here. Now the question is, are the two distances we have going to be equal to each other, or are these two distances going to add up to be a third distance? Some distance problems, these two are going to add up to be a third distance. But we don't have a total distance that they're going to add up to. However, since both runners did start at the same spot, and the second runner caught up to the first runner, and that was at the same spot, same instance, they both ran the same distance because they both ran the same path. So the distance the first runner ran plus the distance of the second runner has to be equal. So here's the distance of our first runner. Here's the distance of our second runner. So we need to go ahead and solve that for t. And we get a quarter. A quarter what? A quarter minute or a quarter hour? Well, we said our rate was in miles per hour. We made sure our time right here was in hours, so this would be a quarter of an hour. If you did want to, you could go ahead and change that to minutes and say 15 minutes. Either one would be fine. It doesn't make a difference. Now, when you're dealing with these applied problems, what we have right here are typically going to be the formulas that you'll end up putting at the top of your charts. Gallons times miles per gallon equals miles, if that's your situation. The percent of solution times the amount of solution equals your pure amount. Or if you're dealing with distance, it'll be rate times time equals distance. Or if you're dealing with work that gets done, it'll be rate times time equals work. Sometimes it may be price per item times number of items equals your total cost.